So we're continuing with that arrangement of 5-minute summary talks from our 6 speakers coming up in the even, if you wish, we're going to be broadening the spectrum and messengers out of the universe. And we're going to have those 6 presentations, and they're going to be followed by 15 minutes discussion and Q&A along the same lines that we've done for the EM astronomy session. So with that, I'd like to introduce Michael Coughlin. He's faculty at the University of Minnesota, and he's going to be giving us an overview of machine learning in the multi-messenger era. Take it away, Michael.
Okay, can everyone hear me?
Yep.
Great. Okay, so I have the both wonderful and awful task of attempting to explain all of the ways in which machine learning is truly changing how we're doing multi-messenger astrophysics. So this is, my talk was a very brief overview of many of the myriad of ways in which this is happening, and so I will just give a very brief summary here. Let's see, can I change slides? Slides, okay, well, it's not a good start. There we go. All right, so this slide is for motivation. So we talk a lot about how gravitational waves and their counterparts are truly changing how we're thinking about astrophysics. And so on here, I'm just highlighting a couple of the ways in which it's been proposed and it's been done in terms of how we're using these counterparts. And so on the top left-hand side here, we have, for example, the Hubble constant, so the measurement of the expansion rate of the universe. As many of us know, there's kind of a there's open issue in cosmology where, depending on how you attempt to do this this measurement, you get different answers at the sort of 5 sigma level. And so one of the great aspects of gravitational waves is that they provide yet another way to do these Hubble constant measurements, and have been proposed to be one of the ways to, let's say, mitigate the tie between these two. And so after many more observations, it's very likely that we'll have yet another important and percent level probe of this expansion rate. On the right-hand side here, I highlight something from nuclear physics. So, so neutron stars are really excellent probes of some of the densest matter in the universe. And so, laboratory measurement, it's something that laboratory measurements here on Earth simply can't get at. And so, it's already been shown through the binary neutron star event from a few years ago that a combination of not only the gravitational waves, but also pulsar mass measurements, in addition to the gravitational wave counterparts, taken all together, can strongly constrain, for example, the radii of these neutron stars, which tells you quite a bit about how this dense matter is behaving in these compact objects. Finally, and there's again many more science cases for which is the case, but testing general relativity. So again, from this binary neutron star event, we could measure the time delay between the gravitational waves and this electromagnetic signature, which allowed us to pretty strongly constrain GR in this strong field regime. And that it ended up, placing quite strong constraints on any theories that go beyond Einstein's theory of general relativity. And so this is just a few ways in which multi-messenger detections are really driving the science that we can do with these compact objects. Okay, so what's the problem? That sounds great, right? But there's a long way to go between the gravitational waves and these counterpart identification. And in my talk, I walked through this right-hand side here where you start with the gravitational wave strain, you need to calibrate and clean it, you need to make the gravitational wave detections, you need to localize and classify the signals, and then put out the alerts. And then you need to go look for them in using your telescopes. And so and there's a variety of ways to do this, but broadly you'll get many, many candidates, as been talked about in these astronomy talks, and you get photometry and spectroscopy to follow it up. You can identify the signals and you characterize it. And so in my talk, I walked through, many papers and many analyses that are truly being changed in every step of this process, how machine learning has contributed to that. And so to close, I just wanted to highlight a few areas in which I think, which I'm really excited to see machine learning push forward. And so for the first one, gravitational wave inference, where we estimate the source parameters and sky location of the gravitational waves, tends to be a very slow process. It can take many hours to days, and it's already been shown by even some of the people who are giving talks today that using binary black hole signals and combined with machine learning applications, inference can be sped up by or literally orders of magnitude. And so this fundamentally would change how we think about doing these counterpart follow-ups when you have gravitational wave counterparts that are fading on the order of a day time scale. Saving these kind of hours truly can make a difference. But the question remains, most of these have been applied to these very short binary black hole signals. Can it be applied to these long binary neutron star signals where you in general expect to see these counterparts? I think the second area that I'm excited to see is, can machine learning provide optimal follow-up strategies to rule in and rule out specific transients as sources, given that our follow-up telescope time and sensitivity is limited? And so there are a number of talks today that will be about classifiers. We've already heard one of them, where you take full photometric time series and you attempt to classify the signals. There's also talks on brokers and schedulers and everything else. But I think that their open question remains, given, for example, a night or two of data from one of these wide field of view survey instruments, can machine learning provide us basically strategies or the required follow-up resources to prioritize how we use that time? Finally, kind of looking even further ahead, sort of one of the key goals of multi-messenger astronomy is to combine data sources from multiple, from these multiple data streams. And so, I think that there's ongoing efforts from both the gravitational wave and the EM communities to build inference pipelines to extract information about the masses, the spins, and the equation of state. But sort of the holy grail of this is to do joint inference to, for example, measure the equation of state of neutron stars using both the gravitational waves and optical data. And so can we use machine learning to basically make the inference fast enough to make this possible? Because right now, it's all done separately. Okay, thank you.
Very good. Thank you, Michael. As a reminder, of course, we're holding on the question session for the end. I think now it's time for our second presenter in that session, who's going to be Ashley Villar, a postdoctoral fellow at Columbia. Ashley, when you're ready, please take it away. Who's going to be talking to us on a new supernova light curve classifier. Thank you.
Yeah, so my name is Ashley Villar. I'm starting a stopwatch so that I don't go over 5 minutes. So yeah, I'm going to tell you about, I'm somewhat going to tell you about this new classifier we presented in a new paper called SuperRain, whose goal scientifically is to classify supernova light curves into various core collapse classes. So one of our focuses is the fact that it can distinguish between many subtypes of supernovae. And the second fact is that it's been trained on real data as opposed to something like the plastic data set, which is a wonderful simulated data set. I think for this 5-minute summary, I am going to focus on the machine learning. That sounds like from the questions what people would like to know about. But one slide on the physics quickly. So in time domain astrophysics, If we lived in a perfect world, we would grab every photon at every wavelength at every second of time to fully understand the physical picture. The reality is that that's extremely expensive, as it's been mentioned in the context of getting spectra for galaxies. So instead, what we have to do is take broadband photometry, where we bin up many photons and we get a loose idea of the color of this overall black body shape. But luckily that actually those broadband light curves, even if they're not wonderful looking, do encode a lot of the underlying physics. And that's really, that's what we're relying on to classify them into their physical subtypes. So this is more like a realistic light curve that we will expect to get in the future from this new observatory coming online that I hope everyone has heard of, the Vera Rubin Observatory. For the context of this talk, it's just going to be a transient discovery machine. So it's going to increase our discovery rate by 2 orders of magnitude. So we're going to find 1 million new supernovae and transients every year. So this is really driving a big data revolution in time domain right now in preparation for the launch of VRO in 2022. So very generically, I like to think of the data-driven problems as being needles in a haystack, where needles are the millions of new events that we can't possibly follow up. So we need some type of statistical methods to at least make ensemble statements. But then the needles are, in a way, they're not just the objects that get spectroscopy, they're the objects that actually get human hours devoted to them. And it's an interesting problem to ask, what does that mean scientifically? The ones that we follow in real time must be very valuable. So that's why I spend a lot of time thinking about is how do I classify the haystack and how to identify the needles. So SuperRain is trying to solve the haystack problem. It does this, like I said, using a real data set that's been published now for everyone to use that is similar to LSST data properties. To do this, we build a neural network, which is a recurrent neuron-based variational just autoencoder, which is a lot of words. But kind of the interesting parts of it are, one, the way we pre-process the data is with Gaussian processes, as other people have started to do as well. And we're also following precedent there. So we do that using a 2D GP, which is kind of interesting. I'm happy to talk about. We then pass that through something called an autoencoder, which takes all of that data, and similar to the wavelets that were discussed, it tries to fit it to a model that in a way that we don't have to specify the model itself. We just have to specify that we think we could build this model through a series of matrix multiplications, and that model can be summarized in 10 numbers. That's really the assumption we're making. And then the neural net's job is to figure out that model and to fit the light curves. What's cool about this architecture we came up with is that we actually can append a time number to the encoded light curve. So it actually kind of calls it as a function. So we say, what does the light curve look like in G band at time 0? And it'll build a light curve. So I'm going to show that. I'm just going to skip to the end and show you that it can interpolate and extrapolate light curves entirely based on this neural network. And then the last thing I want to highlight is new work, where we're using the same architecture more or less, but we turn it into a variational form. And what's cool about this is now we're looking for needles in real time, where what we do is we take the plastic simulation, we run it through this neural network, we encode the light curve, and then we run that encoded space, which is shown on the right-hand side, through something called an isolation forest to identify in real time, hey, which light curves don't look like the others? And what's cool is that then you get an anomaly detection score in real time. And so we can use this to identify the needles of Vera Rubin while we're observing and actually trigger early on. So I'll end there. Thanks.
Nice, thank you. All right, time to move on to Kaze Wong, a graduate student from Johns Hopkins, who's going to be talking about a simulation-based gravitational wave population inference with normalizing flow. Kaze, are you online? And
hello, can people see my screen?
Yes, we can.
Okay, cool. I'm going to start a timer so that I also don't overrun. Okay, so let's get started. Hi, everyone. I'm Kaze. I'm from Johns Hopkins University, and this work, it's a work that I actually done with people from CCA, which is Gabriela and Shirley, so grateful for them to get this working. But today I'll tell you how do we use a technique called normalizing flow to do analysis in gravitational wave population. So the idea is LIGO have been founding a lot of interesting events for us. It found gravitational wave, right? That's 5 years ago. And then the first two observational run, they found 11 events in total. So you have some distribution on the mass plane on the left, and you have some distribution on in spins and mass ratio on the right. And in the newest LIGO observational run, we have 56 candidates announced on the public database now. So the number is racking up. It's really important for us to think ahead, like, okay, once I have a population, what kind of physics I can learn from it, right? And as any physical problem, you need to build a model for your population and trying to understand, okay, how do I connect my observable to my physics? And this is an oversimplify of data analysis before I go into the gist. You have some data, right, which is your observable, your gravitational wave, your mass spectrum or something. And you build a model, which is a likelihood function that you use. And hopefully together combined, you have some posterior, you have some constraint on the physics that you care about, which is parameterized by a probability density function on the physics parameters, let's say lambda. Okay, so to put this into context, the observable could be the distribution of an event. And the result is paper, citation, whatever, like these kind of products. And how do you, so the most of the work that graduate student, postdoc, faculty do is into the likelihood, is building the model. Of course, there's instrumentalists dealing with the data for us, that is great. For us, our job is to build a likelihood, to understand the physics from the data. Okay, so how do we do that? And one way that people do it is through something called population synthesis simulation. So these are really complicated simulation. What they do is they evolve a bunch of binaries until they look in the black hole and you count, okay? So then basically creating synthetic catalog from some set of physical assumption. And then they can have, like you count the events that in your synthetic catalog, you can plot a histogram of their mass, which is shown here, which is their primary mass spectrum. Or you can plot the spin, you can understand it in multiple ways. There are multiple simulations doing the same thing. Well, I should try this thing, I think. Sorry. So, and you have different simulation getting these mass spectrum and spin distribution for you. Now the question is, how do we turn this? How do we compare these simulation results to the data? And turns out this is not a super trivial problem. And what's the problem here? The problem is we need a likelihood function. We need some quantitative description of this catalog, right? Which is P of theta given lambda. P is the probability. Theta here is the source parameters. Let's say the distribution of mass, like your two masses, okay? And lambda is something called hyperparameter, physical parameters that describe your universe. It could be supernova kick, it could be like some cosmology or so on and so on. And we need such function to compare our simulation to the data. But the problem with simulation is, first, doing a high dimensional KD is somewhat hard. It's not impossible. It's just, the more dimension you have, the harder it is. The main problem here is simulations are usually expensive. It takes like 3 days or a week to get one. And if you want to work out a constraint on these parameters, you may need 1,000 or 10,000 simulation, which means that you may spend a decade to just try to produce the simulation that you need to do the inference. So that's bad, right? And in my real talk, I talk about how do we use a flow-based generative network. It's a kind of deep learning techniques. The idea is the following. You basically have a Gaussian and you have some tunable transform that you can tune it and wrap around which transform is simple prior that you know how to sample into a complicated distribution, which describes your simulation. And once you train it, you have your function, you have your analytical function. So the takeaway, like, please check out my whole talk, but as a one slide summary, the idea of my talk is with something that is simulation is complicated, you don't know how to write an analytical form, normalizing flow can get you the likelihood function, and you can put that likelihood function in your inference pipeline, and voila, you get your analysis results and paper. So please check out the slides and email me if you have problems. That's it for me.
Thank you, Kaze. All right. Our next speaker is Agata Trovato at the National Center for Scientific Research in France, where she's a postdoc, and she's going to be telling us about neural networks for gravitational wave trigger selection in single detector periods.
Yes, hi everybody, I'm Agata Trovato. I will try to share my screen. I hope you can see it. So I will talk about an application of neural network to gravitational wave data analysis. So let's start with a brief introduction. So in this slide, you see the typical signal we get from the spiral merger rig down of two compact objects, like a binary black hole system of or two neutron stars that produce a gravitational wave. These signals that we look in our data are very weak and rare, and our data have a lot of background, which is complex in the sense that it's not exactly Gaussian. And here in this plot, you see, as an example, the strain noise as function of frequency. You see for 3 detectors, you see that the curve is not flat, there's different various structures. And moreover, there are also non-stationarities. And this plot you see here is a representation of various type of transient noise that we internally call glitches. So this is a typical spectrogram where you see the frequency versus the time, and you see there are different shape, and some of these glitches can mimic the signal. Like, for example, this is the typical signal, is a chirp, and this is, for example, a blip. It's not so different. So there are in literature various method, as one was mentioned in the initial talk, to somehow use machine learning to identify the signal in our data, and they use different kind of representation of the data. In this work, we use the representation as time series, so as we get from the detector. And as it was mentioned in the title, we are focusing on the period when only one detector is active. This is why usually in the typical analysis that we have, the easiest way to reduce the impact of the glitch in our sensitivity is to look for coincidence of signal in multiple detectors, because the glitch usually should be in one detector per time. But of course, you cannot do in a single detector time. So we were wondering if machine learning could be helpful in this case to reduce the amount of background and help the searches that we already have. And this amount of time is not negligible if you consider the different observation runs that we have had until now. So what we are doing is we are using a convolutional neural network as a classifier. We have identified the 3 classes of data. So the first classes that you see here in red is when we have only Gaussian noise, even if it's not exactly Gaussian, so Gaussian-like real data. Then the second class is the noise plus the injection of signal. And the third class is when there are glitches. And as I was saying, the detector is a typical convolutional neural network with convolutional layer and a fully connected layer. This is an example of the confusion matrix that we get, which is quite diagonal. I skipped the discussion on the length of the signal, but the result in this case I refer to this mass range and SNR. So at the end, what you get in terms of if you plot for all the samples the probability to be classified as signal, you will get something like this. And in the next plot, I will use a cut on this probability. For example, here is I highlighted the bin at 0.99. And if you use different cut on this probability, this is the efficiency of the signal classification, for example. And if you use the last, this extreme cut at 0.99 for different scenarios, you have more or less an efficiency around 80-90%. And this instead is the false alarm rate that for the last bin is something 1 every 83 minutes, which is still a lot. It's much more than what we need for our analysis. That's why this could be used at the moment for some kind of trigger preselection, but it has still to be improved. So it's not a final work, but this is an ongoing work. And we are working in this moment to use different metrics in the optimization of the network. And that's all.
Thank you. All right. Again, as a reminder, we're going to taking questions at the end of that session. And our next speaker is Leïla Haegel from the University of Paris. And she's going to be talking about predicting the properties of coalescing black holes for gravitational wave physics. Leïla, I guess we should try to stick to the 5 minutes. We're about 5 minutes behind schedule, so let's try to stick with those 5 minutes. Thank you. Please take it away.
I will. Hello, everybody. So this is a presentation where I'm going to talk about the black holes we detect the gravitational wave from. And when we're talking about gravitational wave physics, we do not have a myriad of events like we have in astronomy, where machine learning is useful in this problem, that it's a high-dimensional event. We're detecting gravitational waves from binary systems of black hole. And that means that initially we have actually 8 parameters that are describing the 2 black holes. There are the mass of the initial black holes and the spin components of the 2 black holes. However, those black holes are merging into a final black hole that has a final mass, a final spin. And it's important for us to be able to infer the final mass and the final spin from the initial black hole. This is important because this is entering our design of gravitational waveforms that are a very important part of the detection and also the analysis, the inference of the source parameters. And it's also something that we use to do some tests of general relativity, etc. So the objective here is to actually use a neural network to be able to infer the final mass from the initial mass. And the reason why I have tried to use a neural network in this case is because right now we're relying on fits that are based on explicit ansatz, to which we're trying to determine the parameters. But this is a method that doesn't scale very well to a high number of dimensions. Therefore, the precession effect when we have the 2 black hole spinnings are approximated. The question was, if we use a neural network, although in this case we do not have a very large catalog for the input data, is it actually bringing some more efficiency, more accuracy to the prediction? And the answer is actually yes. When I'm saying that we don't have a lot of data, what we use as input data are numerical relativity simulations. And those simulations are the most accurate gravitational waveform, but also properties of the black hole before and after solutions that we have to the Einstein equation. However, they are very computationally intensive. And when we look at what we have as catalog from different code, in the end, we have about 3,000 events, even less than that, of which we can classify that about half are for non-precessing black hole and the other half are for precessing black hole. So this is not a huge catalog compared to modern usage of neural network. However, it is still enough to be able to predict with quite high accuracy the final properties of the remnant black hole. In terms of setup, we've used 80% as training data and 10% as validation data, that we use to select the best hyperparameter of the neural network, and also to create a stopping procedure to avoid overfitting. And the final 10% were actually used for the testing data that were used only once when we have chosen our neural network, and to determine the final efficiency that has been published, that is displayed on the article that has been published on classical and quantum gravity this year. And once we have trained the neural network, this is a simple artificial neural network structure. I have tried to use convoluted. In this case, there is not reuse, it's not an image, not or anything. We have 4 hidden layers. We use ADAM, where we have optimized the learning rate and the decay. I've tried a heuristic optimization and also the new automatic tool. In general, these are the best usage. I would say that the current limitation for this neural network is actually the size of the input data. I do not think that this neural network can be much improved from all the tests that I've done. I think we just need more data. And then finally, I'm going to jump directly to the result. I'm trying to use the results, especially for the processing case, because this is a case where we wanted to see if we were having better results compared to the existing fits. And the answer is yes, absolutely. The traditional fits are overestimating the final mass and the final spin, and we have much better accuracy with our network. We're also comparing with other methods that are using Gaussian process for interpolation that are also having very good efficiency. We're seeing that we're slightly better for some cases, and we're trying to understand this as I am implementing the software in the LIGO algorithm library. That is an open source software. So once it will be reviewed, it will actually be available to be used by everybody in astrophysics. Thank you, and looking forward to answer all your questions.
Thank you, Leïla. And our last speaker for the session is Gautham Narayan, and from UIUC, if I'm not wrong, Gautham, who's going to be talking to us about looking at the sky with artificially intelligent eyes. Take it away, please.
Great, thank you. So to start with, I want to emphasize the point that Michael made earlier. You can't classify supernovae and multi-messenger events entirely from their full optical light curves. The problem is these things are very fast, and if you have to wait for the full light curve to classify an event, then, well, you've missed the event. You haven't been able to schedule follow-up studies with spectroscopy. And you really do need to catch these things very, very young. That's when you learn about their physics, in particular the physics of the explosion. So if you want to do things like connect the gravitational wave signal to the EM signal and understand the equation of state of neutron stars, you really need that early time data. If you can't use the light curve, then you have to use contextual information. And so that leaves you with trying to get redshifts for a whole bunch of galaxies, which is critical for GW170817. As a community, we got really lucky that it was in a galaxy that happened to have a redshift and was reasonably well studied. But we also have things like host morphology from deep stacks of the images. And I think this will be particularly critical as LIGO becomes more and more sensitive. We've seen plenty of binary black hole events, but we should expect in the next decade that we'll start to see co-collapse supernovae in gravitational waves as well. And so we want to identify those kind of events soon. That means if we have to use contextual information from the host galaxy, that we need to sort of assemble a training set that includes not just explosive transient light curves, but explosive transients in context, in the host environments. And so I've been working with Alex Galeano, who's a third-year grad student and an SF research fellow here, to invert this problem. What can we learn about transients from their galaxies themselves? Alex has built a large pipeline that has the ability to sort of automatically take any new transient associated with a host galaxy, but he's also been looking at the properties of those host galaxies. And what we've been finding is that it seems like different kinds of transients live in different kinds of galaxies. That's particularly useful because if you don't have the full light curve, but you do have a deep stack image of the galaxy, then you can use the galaxy to maybe improve the classification of the transient event. You can use it when the transient's very, very young. And while this is not the most accurate deep learning set out there, it's only about 70% accurate on just the galaxy information. That is, I would still argue as an observer, better than random guessing. And I'm okay on occasion pointing a spectrograph at the wrong target and getting something not terribly useful if 70% of the time I do get something useful. So Alex's data is public, and it's hosted here at NCSA at that URL on the slide. It has something like 14,000 supernovae and the host galaxy properties, spectra. You can download all of this data. You can also install his entire pipeline. It's pip installable. So pip install astro_ghost, and you're off and running. But we want to do more than just get all of their properties. And unfortunately, galaxies don't often have spectroscopy. So we're going to try to find host galaxies in images, but then we need to have some sense of how far away they are. And so we need to know redshift information. To do that, obviously with something like LSST, there's no chance of getting spectroscopic redshifts for everything. So we're going to have to rely on getting redshifts out of the broadband photometric information that we collect from LSST. Another student of mine, Andrew Engel, who graduated just this past May and is now a data scientist at PNNL, used a neural network architecture initially developed by Joanna Pasquet. This is actually fairly similar to what Dimitrios showed you earlier for classification, except here being used to get a photometric redshift probability distribution function. And he trained it on photoz's, not just from SDSS, but using PanSTARRS data, using UV and IR data to sort of improve its performance. And improve its performance it did. So sort of traditional photoz methods are shown here on the right-hand panel. And you can see they're pretty darn good. The dispersion is pretty low, but Andrew's CNN method is on the left-hand panel. And you can see that his median absolute deviation is lower. His scatter and bias is lower. So this is a pretty promising thing. We are finishing up this work, but it's already being used in a live survey. I'm part of an experiment called the Young Supernova Experiment to go try to find young supernovae. And Andrew's code runs on the host galaxies that Alex's algorithm identifies for every single transient that we find either in the ZTF public data or that is reported to the transient name server. And finally, of course, there is still a role for light curve morphology. And so with Daniel Muthukrishna, who's a grad student in his final year at the University of Cambridge, we developed this as an offshoot from the plastic survey, and we called it Real-Time Automatic Photometric Identification, or RAPID, which is very, very clever. And the idea here is that we use a LSTM network with gated recurrent units to classify light curves as they come in, as we get each observation. So we do some pre-processing to sort of Gaussian process smooth all of the light curve that we can see, but with every single measurement that we get, RAPID sort of reclassifies the event, and so it gives you a classification as a function of time, which is very, very distinct from a lot of the other classifiers that you've heard about thus far. So initially you can see that RAPIDs identify this particular real event from ZTF as pre-explosion, but as it gets more and more observations, it decides that the object belongs to a specific class, in this case, that it's a TTE, which it in fact correctly classified. And so this is also written up as a paper that's on MNRAS. You can also get the RAPID code off of pip. So pip install astro_rapid. We're not very creative with our package names. And feel free to start using it. The core for us and what we're working on right now here at Illinois is combining these techniques together. So one single classifier that takes the host galaxies, takes the light curve, spits out a redshift, spits out a classification for the transient using both the light curve morphology and the host galaxy morphology. And so that is something that hopefully will be out in a couple of months. We expect to be using it as part of Yeezy and also in LSST as part of the Plastic 2 challenge, which I'm currently leading up, and within the Supernova working group that I'm the lead for. And with that, I'll stop.
Thank you, Gautham, and all the speakers of this session. And let's press ahead with Ashley. Do you wanna read your question, or shall I?
Yeah, I'm happy to read it. This is just for Gautham. Hi, Gautham. These are really cool. All three were really awesome projects. I'm wondering for the middle Andrews project, just if you have any idea how it'll perform at higher redshift.
It starts to fall apart at Z of 0.6 right now, mostly because so much of the data is dependent on pan-stars, and pan-stars itself starts to fall apart at that redshift. You have, of course, seen more than your fair share of pan-stars images and understand all the artifacts and data quality issues that survey has. Ultimately, I think we'll replace it with LSST itself, but obviously we can't do that quite yet.
All right. Any other hands? Erik, why don't you go ahead?
Yeah, the question, Gautham, is what are the required timescales to go and learn about this interesting physics at early times? Suppose that a gravitational wave is detected and they let you know. What is the latency that you require to adjust your telescope and go and capture that precious light?
So currently, the latency is effectively something like a day, right? That's about as fast as we can turn around and point another telescope at any given source on average. There are some objects where we can do considerably better. So, for example, Ashley's colleague at Harvard, Griffin Hassan-Zadeh, did this beautiful work on 17 CBV, where he was able to use the Las Cumbres network of telescopes to get 15-minute cadence observations on this one object. But those are one-off things. I'd like that to become regular, because I think you sort of want the few hours right after explosion. And this is going to, of course, depend on the class of transient, but since we're in the MMA section, I'm mostly focusing on the MMA here. If you are interested in something like a type 1a supernova, you might want the first 4 days after explosion. That's where, for example, we can see a signature if it's interacting with a binary companion that is a main sequence star versus a white dwarf. So timescale depends on class, but ideally few hours, and we'll start to really be doing well. And that's not where we are right now.
Any more questions for our speakers? Maybe I can ask one. Ashley, if I remember well, in your presentation, you hinted that there is a benchmark set that the LSST is using for comparing methods. Did I gather this right? I think all in all, this is going to be fantastic if somehow, even collectively, and surely I have in mind, of course, gravitational wave physics as well, because many of our presentations today touched upon gravitational wave detection, classification. I think it's going to be quite important in the field as we move forward in accepting some benchmark tests that at least methods and various teams should run their algorithms on. Maybe I should let you speak and tell us what is happening with LSST on that front. And
Yeah,
if I have that right.
Yeah, I definitely, good, yes. I was about to point out, Gautham, I think, is actually the person who's really leading this, but you're definitely right. I think there has been an issue of a lack of a baseline data set for which we can compare our models. Luckily, and all these talks reflect this, models are increasingly open source, and so anyone can pip install basically everything that's been discussed today. So the plastic data set is, to me, really now should be the gold standard. So it is a simulated data set from the community of many models that has been run through a LSST simulation. So it is our best guess at not only what the data itself will look like, but also the biases that exist in our data set, given our observed set of transients right now. So yeah, I was additionally just pointing to, we've also now released the Pan-STARRS medium deep survey data set, which is a collection of 5,000-ish transients that have a similar cadence, filter set, and depth as LSST, but about 1/1000th of the discovery rate. So I think that's a nice complementary data set because it is not as large as plastic, but it at least contains kind of the uncertainties that real data contain.
Good. Gautham, sounds like you have more to add into that.
Yeah, so it was always the intent for us to make plastic the benchmark gold standard data set for this job, but it is incomplete. Let's make no bones about it, right? There are something like 15 classes of transients in there, and I appreciate Ashley's point about, real data versus models. A lot of the plastic models are, of course, based off of real data, but they can't all be. We have one EM kilonova. you can't build a model off of that. So you have to go talk to a theorist. And so we're doing things right now to update the set of models and make plastic a better resource for the community as part of this Plastic We Do. So for example, Deep Chatterjee, who is an Illinois Survey Science Fellow and is on this call, he's currently updating the Kilonova model that we have from Dan Kaysen's model to these Bulla models that in fact Michael Coughlin put together on GitHub. We're also trying to include other sources of transients. And so we'll be incorporating all of those MDS light curves that Ashley described from her PanSTARRS data. But if you have a pet class that you really care about, say tidal disruption events or flare stars or T Tauri stars or whatever it is, please get in touch with us right now. Over the next 6 to 8 months, this is when we have to update these models in preparation for the next version of the Plastic Challenge, where we will be, instead of sending out full light curves, we'll actually be sending out an alert stream. And instead of just light curve observations, so magnitudes as a function of time, we hope to be actually sending out pixel level data so you can look at the actual PSF in a realistically associated host galaxy, which is connecting up what Alex has been doing.
Let me, since I brought this up, let me make a remark here that generally I think engineering and computer science disciplines have been paramount in setting up benchmarks and reference data sets because, you know, it is also very much connected to industry. And I think all in all, we've raised that aspect, of course, for LSST, but I'm thinking also in terms of gravitational wave physics. And I don't know, off the top of my head, how many outside the nominal LIGO, Virgo, let's say, community are participating in this workshop. This is probably something that we should be considering, namely setting up some benchmark set as the community as a whole gets their hands into, you know, gravitational wave data or LSST data, so that we make sure that, you know, we compare apples to apples and, you know, we make choices that are gonna, you know, make sense both computationally and scientifically. All right, I see, first of all, we have 5 more minutes from, borrowed from Phil and his session. So let's stay on any additional questions. And I think, John, maybe you have a question for Ashley. Do you want to take it live?
Sure. Sorry. Sure, yeah. I just wanted to ask, I can't remember if you mentioned that you were going to augment your model, the Super RAENN, with variational autoencoders, and if so, would that be able to sort of reduce the Gaussian process pre-processing step, which I assume could be the expensive part?
Yeah, that's a good question. That's very technical, but so the variational part, well, so you could do this, but I would argue, so we use the Gaussian processes specifically so that we get a flux measurement at every point in time, which we found was just the best way of training our autoencoder. So GPs are wonderful at interpolation, but don't do great at extrapolation, which is pretty well known. So I think that will continue to be the way that it works, is that they work together to do one which mainly thinks about extrapolation and one which is working on the interpolation step. Yeah, and then I guess to add, so a concern is that GPs are quite expensive but they scale with the number of data points in the light curve, not with the number of light curves. So actually in our case, our light curves only have a few hundred data points at most. So it's actually very inexpensive. I will also mention another expense is choice of kernel. So specifically because we're using a 2D kernel in wavelength space and time space, but actually Celerite is this like hyper optimized Python code by Danforth and Mackey that is about to include 2D arbitrary kernels. So that will be a huge speed boost as well.
Very cool. Thank you so much.
All right, and I think probably we should give Phil the last question of the session to Kaze.
Kaze, yeah, so a question about your normalizing flow models. Do you envision a larger scale training using like a hybrid of data and simulation?
Can you clarify on what you mean by hybrid?
I mean, so the point being is that normalizing flow you can train on data, right? But you might be missing or, you know, adding additional effects that are not necessarily reflective of your data, of your signal, right? So you can do a combination of the two.
Yeah. So the idea of my work is like you have your simulation that you understand pretty well, Then you use a normalizing flow to understand that simulation. Then you go to go to compare with the data. The data actually compare with the normalizing flow using whatever traditional sampling method that you like. So on that hand, you get it absolutely under control. Does that answer your question? So like the most of the training is done with the simulation. So that part we understand.
Yeah, it's sort of. Yeah, just a quick follow-up. How long does your training take?
Depending on the size of your simulation. So if your simulation is 300 gigabytes, it's going to take a little longer, maybe a week. But usually the data set that required to train a competent a model is around maybe 10 gigabyte, and it converts pretty well even for pretty high dimensional data set. So I would say you take a day or two to train a production level model.
Okay, thank you.
Well,
All right. I guess with that, let's thank all the speakers of this session. And Phil, on to you.